Welcome everyone to another session of supplementary videos, and today we will be discussing some mathematical ideas. So we will begin with a very important concept that we use in statistical mechanics quite a lot, and that is the idea of Stirling's approximation. Okay, so we will be discussing what Stirling's approximation is all about. So what Stirling approximation basically, so it's, as you can say, think about this is an approximation, and what it approximates is it approximates the natural logarithm of the factorial function for large numbers. Okay, so let me write down the approximation first. So let's say what Stirling approximation says is take the log of n factorial. This is approximately equal to n log n minus n. So this is what Stirling approximation is all about. Okay, and this is valid. This result gets more and more accurate as n becomes larger and larger. So this is valid for n much greater than 1. The result becomes more and more accurate as n tends to infinity, basically. Okay, so this is what Stirling approximation is. Let's see how this comes about. So if you think about n factorial function, so what it is basically a product of 1 into 2 into 3 to 4 dot 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 up to n minus 1 into n. So this is the product of n natural numbers. Okay, and if you take the logarithm of this, you get log of n factorial, which is basically log of the product of all the natural numbers, let's say till n. Okay, and if we use the identity that log of the product of two quantities is equal to log, we can write it in this, so the product becomes additive. So if we apply it for all the n terms, this we can write this equation as log of n factorial equals log 1 plus log 2 plus log 3 plus dot 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 log n, or we can write this as in a summation notation. So n factorial is equal to sum over, so this is, if you see, log of a running index, let's call that key, and that key runs from 1 to n. Okay, so till here you see, like, this is no approximation till here because we just used the definition of factorial function and took the log of both sides and wrote it in a summation notation. Okay, here comes the approximation that we want to do. So as n gets larger, as n gets bigger, the sum k is equal to 1 n log k can be approximated by the integral, okay, of log x dx, okay, from 1 to n. Okay, so this is where the approximation comes. So what we do is we approximate the sum by an integral, and this approximation becomes better and better as n becomes larger and larger. Okay, so if we write that, then we have log n factorial is approximately equal to the integral of 1 to n log x dx. Okay, and using the fact that the integral of log x dx is x log x minus x, and this comes from integration by parts. Okay, and so if we know, so this is, if you see, this is the indefinite integral. So if we use this here for our definition, it becomes log of n factorial is approximately equal to x log x minus x limit from 1 to n. Okay, if we use this limit, this will become n log n minus n minus 1 log 1 minus 1, and since log 1 is 0, so this becomes n log n minus n plus 1. Okay, and since as n gets larger and larger, this 1 becomes basically negligible, so therefore we can write log of n factorial is approximately equal to n log n minus n. Okay, so that is what Stirling approximation is. Yes, and this is used, this is the most frequent expression that we used in statistical mechanics, by the way, where we, because in statistical mechanics what we do is always we start by counting the possible number of possible ways. So we are doing a lot of permutations and combinations, and there we have a lot of factorial functions. So this expression, what it does is it converts a discrete factorial function to a continuous one. Okay, and the moment we do that, what happens is we can use the rules of calculus. Okay, and that makes lot of that makes the job a lot easier, because it's always easier to handle smooth functions rather than discrete functions. Okay, so that's all about Stirling's approximation. It's used quite a bit in statistical mechanics. Okay, so now we move on to the next concept of today, and that is the idea about the method of Lagrange multipliers. Okay, so this is the next topic for today, that is the method of Lagrange multipliers. And what this method is used for, so to understand this, let's recap our understanding of, let's say if we want to find out the extremum of a function, let's say the extremum of a function, okay, let's say of two variables, just for example it could be extended to arbitrary. So this is a function whose extremum we want to find out, and if you want to find out the extremum of this function, the condition that we use is the partial f partial x equals 0 and partial f partial y equals 0. Okay, what the method of Lagrange multiplier does is basically extend this idea of finding out the extremum of a function, either maximum or minimum, but subject to a constraint. Okay, so what this method of Lagrange multiplier does, Lagrange multiplier does is to provide a method to find the extremum of a function subject to a constraint. Okay, subject to a constraint. So that's the what the method is. So now when we are having a function, for example here, so now what we want to do, the general problem is, let's say we want to find out the extremum of this function f of xy subject to the constraint that the function, let's say g of x comma y equals constant. Okay, so we want to find out the extremum of this function, but there is a constraint equation between x and y. So x and y are no longer so like there is a relationship between x and y that needs to be satisfied, and this belongs to the class of an optimization problem actually. So okay, so what we are actually solving is an optimization problem here, optimization problem with constraints. Okay, with constraints. Okay, so let's see what this method is all about, and we will generalize this idea. Okay, So let's say we want to minimize, let's say we want to, it could be anything, it could be maximize or minimize. And so let's say to find out the stationary points of the function f, which is f of xy, what we do is we do df. What is df in terms of, we can write it in terms of the partial derivatives, dx plus partial f partial y dy. And since we want to find out the stationary, that means locally the function does not change. So that is the condition that we are looking for. Okay, so if dx and dy, let's say, were independent, if they were independent, okay, then you'll see for this to satisfy, what has to do is partial f partial x has to go to 0 and partial f partial y has to go to 0 individually. Okay, so that's the, from basic calculus we understand that the first partial derivative should go to 0. Okay, but now let's say we have a constraint. Okay, so say we have a constraint that is given by g of x comma y equals c, let's say. Okay, so given this constraint, that means there is a relationship between x and y. Okay, so that's the, okay, so that means there is a definite relationship between x and y given the constraint, and constraint given by g of xy equals c. So there is a relationship between x and y. Okay, so if this needs to be satisfied, given that this is a constant, that means if we take the differential of g, that has to go to 0. Okay, and what is the differential of g? We can write that partial g partial x dx plus partial g partial y dy, and that should go equal to 0. Okay, so now let's say if we use, let's call this equation 1 and let's call this equation 2. So if we use equation 1 and 2, we can write it in this way using an arbitrary, we'll see, called lambda. So what we can do is we can write it in this way, d of f plus lambda g, and that will become, this will become df, which is given by partial f partial x plus lambda times partial g partial x dx plus partial f partial y plus lambda times partial g partial y dy, and this is equal to 0. Okay, so here lambda is called the Lagrange multiplier. Okay, multiplier, and remember that this is unknown, this we don't know yet, so this needs to be figured out, so what that lambda is. Okay, but given equation 1 is true and equation 2 is true, we can write a general expression like this for an arbitrary lambda, which like we can write this condition for a particular lambda, not arbitrary, or a particular lambda that satisfies this expression, and we need to find out what that lambda is actually. Okay, and that is a Lagrange multiplier, by the way. Okay, so basically if you see, that means if dx and dy are to be independent and arbitrary, then for this equation, for equation 3 to hold, the coefficients of dx and dy themselves has to vanish. Okay, so that means partial f partial x plus lambda partial g partial x should go to 0. That's equation, call that A. And partial f partial y plus lambda partial g partial y equals to 0. That's equation B. Okay, so given these two conditions needs to be true, okay, for a particular lambda, so using equation A and equation B and using the constraint relationship, which is g of x comma y equals c, so now you see we have three equations for the three unknowns that we need to find out. Three unknowns. And what are those three unknowns? The three unknowns are the lambda, the value of x, and the value of y, where we want to find where the function is at its extremum. Okay, so that's a general idea about how to find out let's say a function optimization problem given a particular constraint. Okay, so let's do an example just to get this idea better. So let's say you have been given a function g of x comma y equals 1 plus xy, and we want to find out, let's say, the maximum of t subject to the constraint x square plus y square equals 1. That means you're not allowed to move outside the unit circle. Okay, so what we want to do is we want to find out the maximum value of this function t, provided that x and y always stays on this circle, and that circle is a specific circle, that is the unit circle. Okay, this is a circle of radius 1. Okay, that is the condition that we need to find out. Okay, so let's see how to do this. So what we will do is we'll write the condition. So we have one constraint. This is the constraint equation. So we can write all these equations A, B, and C for the specific case. So that will become partial t partial x plus lambda times partial g partial x equals 0, where let's define g. What do we mean? So g of x comma y is basically x square plus y square minus 1. Okay, so that's the circle. So g equals 0 defines the unit circle. Okay, that's the constraint. So partials, if you see from this equation, partial t partial x becomes y plus lambda, and partial g partial x will become 2x will come here. So we will have 2x equals 0. Okay, so let's call that equation 1. And similarly we will have partial t partial y plus lambda partial g partial y equals 0. And if you see, partial t partial y will become x plus lambda, and partial g partial y is 2y, so this will become 2 times y equals 0. That's equation number 2. Okay, and remember we have the constraint equation itself, which is x square plus y square equals 1. So that's equation number 3. So using all these three equations, what we can find out is, so from equation 1 we can see, from this equation we can see that we can write y equals minus 2 lambda x, and from this equation we can write y equals minus x by 2 lambda, and if we equate these to y, we can solve for lambda. That will become minus x by 2 lambda equals minus 2 lambda x. So if we solve for lambda, we will get lambda equals plus or minus half. Okay, so we figured out what lambda is. Okay, so if you see, if lambda is plus or minus half, and if you substitute it right here, what we will get is, so if lambda is plus or minus half, y is, so if lambda is plus half, so you will get y is minus x, and if lambda is minus, this will become plus. Okay, so So let's say we have y equals x. So for the y equals x, the critical points will become, and given that we know x squared plus y squared equal 1, so this will become, x will become plus or minus 1 by root 2, and y will become plus or minus 1 over root 2. Okay, and similarly for the condition y equals minus x, we'll find out that x will become minus plus 1 over root 2, and y will become plus minus 1 over root 2. So we found out all the critical points with all the combinations with x, y for plus minus 1 over root 2, and you see these two critical lines lie on y equals x and y equal to minus x. If you remember the diagram, so that means, so that's the 45-degree line, y equals x, this is y equals to x, and similarly this is another critical line, y is equal to minus x. So wherever the extremum is happening, it will lie on either these two lines. Okay, so these are the critical points that we found out, plus or minus 1 over root 2 both in x and y. Okay, and now if we just substitute the values of x and y, we will find out that t of xy is max at y equals x equals plus or minus 1 over root 2, and the value of t max is 3/2. So that means temporary, or let's say t is maximum on these 2 points along this line. Okay, and specifically on these 2 points, and the maximum value of t is 3/2. Okay, so that's an example of a optimization problem where we figured out, we extremized the function t subject to a given constraint. Okay, so this idea could be explained to, or could be extended to higher dimensions. Okay, higher dimensions where we have, let's say, a function of 3 variables. Okay, so let's say the method of Lagrange multipliers could be extended to higher dimensions. The only condition that we need to keep in mind is that the number of constraints should be less than the number of variables, the independent variables that we are differentiating with, to prevent it from becoming over constrained problem. Okay, so that is a general thing where it works. So let's say you want to find out the function f is equal to f of x plus comma y comma z. You want to find out where, when, or where is, or let's say, let's pose the problem like this: find the stationary points of f subject to the constraint. Now let's say we have g of x comma y comma z is equal to c1, and we have another constraint h comma x comma y comma z is equal to c2, where these two are constants. Okay, so now we have two constants. So what we need to do is we need to find the stationary points of this function f subjected to these two constraints. Okay, and if we just extend our previous idea, the equations will become partial x respect to f plus lambda g plus mu h, and then that will become partial f partial x plus lambda partial g partial x plus mu partial x partial h partial x equals 0. So this is now equation 1. Similarly, we can write expressions in the y and the z direction. So this will become f plus lambda g plus mu h, and this will become partial f partial y plus lambda partial g partial y plus mu partial h partial y, and that is equal to 0. That's 2. And similarly the third dimension, partial with respect to z, f plus lambda g plus mu h equals partial f partial z plus lambda partial g partial z plus mu partial h partial z, and that goes to equal to 0. So these are the three equations that we got from the constraints. Okay, and using these three equations, so equation 1 plus 2 plus 3 plus the two constraint equation which we have, so g of x comma y comma z equals c1 and h of x comma y comma z is equal to c2. In we see we have a set of 5 equations that we need to solve for 5 unknowns. Okay, and what are the unknowns? The unknowns are, you see, lambda, mu, and the points where the function is stationary, x, y, z. Okay, so these forms a closed set of equations where we can solve for lambda, mu, x, y, and z. Okay, so that's the general idea of the method of Lagrange multipliers. Okay, so we saw an example where with one constraint, and we generalized the idea to any like a higher dimension, a function of 3 variables with 2 constraints. So this could be generalized to 3 dimensions. The only thing that needs to be kept in mind is that the number of constraints should be less than the number of independent variables. For example, here there are 3 independent variables x, y, z, but we have only 2 constraints. Okay, so that's if that thing is true, we can use the method of Lagrange multiplier to do our optimization problem. Okay, so that's for this segment. So we will see you in the next segment. Okay, so thank you for being there, and we will see you in the next segment.